Okay, welcome to your last video lecture in Chapter 6, in Section 6.6 on the convolution integral. Okay, so sometimes it is possible to identify a Laplace transform, big H of s, as the product of two other transforms, big F and big G, that are common Laplace transforms for functions that we know, like little f of t and little g of t. It's natural to guess that if we tried to take the inverse Laplace transform of h, because h is the product of big F and big G, that the inverse Laplace transform would be just the product of little f and little g. However, much like the product rule in Calc 1, this is not the case. So in this section we will define a generalized product that will allow us to take the inverse Laplace transform of the product of big F and big G. And so here is our result that allows us to take this inverse Laplace transform. So assume that big F is the Laplace transform of little f, and big G is the Laplace transform of little g. Then big H is the Laplace transform not of the product of little f and little g, but of this integral here. Okay, and so either you can look at the first integral, which is the integral from 0 to t of f of t minus tau times g of tau d tau, or the other way around, f of tau times g of t minus tau d tau. This function, little h, is known as the convolution of f and g, and the integrals above are known as convolution integrals. And this is referred to here as the convolution theorem, one of my favorites. Okay. So for notational convenience, we write the convolution of f and g as f star g, to sort of make it look like a sort of generalized product. The following are elementary properties of the convolution operator, many of which are the same as ordinary multiplication. So for example, f convolved with g is the same thing as g convolved with f. You can distribute f via the convolution operator. F convolved with g convolved with h is the same as f convolved with g convolved with h, which is the associativity law. And if you convolve f with 0, you end up with the 0 function. And so let's apply this to an example. So let's look at the initial value problem, y double prime plus 2y prime plus 2y is equal to sine of t with homogeneous initial conditions. If we take the Laplace transform both sides, we'll have the characteristic equation times big Y is equal to the Laplace transform of sine of t, which is just 1 over s squared plus 1. If we divide both sides by 1 over s squared plus 2s plus 2, we end up with this expression for big Y, which we can write as some function h of s times some function big G of s. We know that h is the Laplace transform of e to the minus t times sine of t, right? If we go over here and write this as 1 over s squared plus 2s plus 1 plus 1, and we complete the square on the bottom, we have that. And we know that g, we've already taken the Laplace transform of sine, so we know that g being 1 over s squared plus 1 is just the Laplace transform of sine. Then our solution y is just the convolution of these two guys here, okay, which is given by this integral. The integral from 0 to t of e to the minus t minus tau sine of t minus tau times sine of tau d tau. In the previous example, we showed that finding the solution of the initial value problem amounted to finding the convolution of the inverse Laplace transform of this function h, which is 1 over the characteristic equation of the homogeneous equation. This guy here, the reciprocal of the characteristic equation, is called the transfer function, okay? Especially so in the engineering literature. And so to find the solution in this particular case, we just had to find the convolution of the inverse Laplace transform of the transfer function with the forcing term. If we look at this in general, so we take the general initial value problem and we take the Laplace transform of both sides, we end up with this equation for big Y, which is just the transfer function h times the output associated with the initial conditions and the transfer function multiplied by the Laplace transform of the forcing term. And so if you convolve both of these, the solution you can see is just the convolution of the inverse Laplace transform of the transfer function with the initial conditions and the convolution of the inverse Laplace transform of the transfer function with the forcing term. And we can relate this back to the stuff we learned in Chapter 3. This guy here is the solution of the homogeneous problem, okay, and this guy is the particular solution of the non-homogeneous problem. Okay, so hopefully this is a nice sort of general ending to our chapter on Laplace transforms, and we'll see some examples of this in other videos as well. Thank you.